Okay. So hello and welcome again to the podcast series Leaf to Leaf, brought to you by LI-COR, and based off the book titled Hitchhiker's Guide to the Galaxy, which was written by Jason Hupp and Dr. Richard Vath.
They wrote
To a
Hitchhiker's
lesser
Guide to Leaf Gas Exchange.
Oh my gosh, I had
not
such a
Hitchhiker's Guide to the Galaxy. That was in fact written by Douglas Adams.
and far better than what we have produced for you here today. Okay.
You may want to start over on that one.
Yeah, I'll do it that again at a different point. Okay, so again, we are here in part 3 of Hitchhiker's Guide to Leaf Level Gas Exchange, titled Looking Deeper. Right, that is part 3, and as such, I have not a new guest, but a now recurring guest who is very excited to join me here today. I'm here with Dr. Lynch.
Good afternoon, Seaton.
Why don't you go ahead and introduce yourself for those of the listeners who may not have listened to episode 4?
Sure. So I'm Doug Lynch. I'm a principal scientist at LI-COR and focusing on plant physiology measurements. And I've been with LI-COR just over 11 years now.
Awesome. Thank you. For those of you who have not listened to episode 4, go ahead and give that a listen. And also, more importantly, maybe read that chapter. To quote Jason Hupp, it was pretty good, which I'll take. And while I have Doug here trapped from doing his actual job, I need to apologize to him because I set him up to fail last episode with some Dune trivia. Took a quote from Dune, and I was quizzing him. It was actually from the collected sayings of the
Muad'Dib.
And of course, I have no idea what that means.
Of course not. If you would read Dune, you would be intimately familiar with the character named Muad'Dib. But I won't spoil it for you.
I'm an uncultured swine. All of Dougie Fresh's fans should note that he, in fact, was right and I'm wrong. This is the story of my life.
So that made me 100% correct in the previous episode.
As Doug's favorite sports ball saying, batting 1,000. But beside the fact that I slandered. Since I screwed up, how are things going beside that?
Things are going great.
I think you're kind of forgetting that you had some big news recently that you were excited to tell people at the office about.
I did?
Yeah. So for those who don't know, Doug is indeed a sourdough baking enthusiast.
What was my big news?
Not an influencer like you may be led to believe, but you grew some wheat.
I did.
Wheat.
I did
Hard
grow.
T for those who can't, maybe that didn't cut out.
I did grow winter wheat in my backyard.
Yes.
It did not go well. And I ended up getting about a half cup of flour out of my patch of wheat.
That is way more than I've ever.
It was a proof of concept that I now can go from growing wheat to processing and milling for flour. So I will be growing more this fall, actually planting here in a few weeks.
Which I really am. I mean, I understand that normally everything I say is at least should be suspicious of a joke, but it is pretty impressive.
It's pretty fun. Yeah. I mean, I'm hoping I get a decent harvest this year. I had a really good fall. It came up really nicely, and then all of it died over the winter, and I'm not sure why, because I had plenty of mulch to protect it. So I'm not sure what went wrong.
So, this is episode 9. This is chapter
11.
Chapter 11. I knew that.
I had to look it up, too, to see which chapter we were referring to.
Well, because the episodes and the chapters are asynchronous at this point.
Right, exactly.
But this whole chapter is about Mesophyll Conductance. And that's what we're going to be talking quite a bit about today. So it is, in fact, a somewhat dense topic. But Doug, maybe you can simplify some of this for us. So from a measurement perspective, what What is mesophyll conductance?
So the term mesophyll conductance actually describes a series of resistances of the movement of carbon dioxide from the intercellular airspace, which has been discussed a lot in earlier chapters, to the site of carboxylation in the chloroplast. And there are a number of different processes that resist that movement, including a phase change to the liquid phase. And all of those can be collectively lumped into a term called mesophyll conductance.
Yeah, I understand that was a pretty loaded question. I appreciate the 30,000-foot view. So if that's from the measurement perspective, from a biological perspective, how would that be kind of versed differently?
Sure. So it's a pretty important consideration from a biological perspective because the mesophyll, or the site of where the chloroplast are, is where CO2 is fixed in the photosynthetic processes. So understanding the resistance of movement to where the reactions actually occur is pretty critical. So there's some really important implications in the biology to understanding these processes.
We'll return to the podcast after a word from our sponsors. Here at AgriNova Global, we're not just delivering carbon, we're orchestrating a paradigm of integrated bioefficiency. Through our proprietary ChloroSync carbon enablement platform, we leverage multi-vector diffusion harmonics to facilitate precision CO2 onboarding across every photosynthetic stakeholder node within the agronomic ecosystem. By delivering dynamic mesophyll interpolation and chloroplast-centric performance synchronization, we're achieving unprecedented carbon liquidity, empowering plants to convert atmospheric potential into scalable biological ROI. Because when carbon meets clarity, growth becomes exponential. AgriNova Global Food Company, innovation, synergy, amplifying biomass, catalyzing tomorrow. Ugh, that's a lot of jargon. For those who haven't gone through prelims, which is where the last time I did a lot of heavy reading in this regard, what are like the broad implications? Why is this? We've talked about a lot of parameters up to this point. We've talked about carbon assimilation, model conductance, transpiration, and things, temperature, other types of data. Why why is there such an interest in mesophyll conductance?
Yeah, largely. So I'm sure there was a chapter on CO2 response curves,
Absolutely.
and the discussion largely probably focused on fitting parameters from a CO2 response curve. And the default instruments for leaf level gas exchange provide you with the measurements for assimilation or computations and intercellular CO2 concentration, so an ACI curve. And that is the most common data to fit to parameterize some really important enzymatic properties. Mostly I'll talk about the maximum velocity of carboxylation, or VC max, which is a term or a parameter computed from fitting ACI response curve data. And that is commonly done because it is relatively easy to calculate intercellular CO2 concentration.
Sure.
Sure, but the topic today goes a little deeper into the leaf, and the correct variable to fit to calculate VC max would not be CI, because that's not where carbon is fixed. It's fixed in the chloroplast. So it's the chloroplastic CO2 concentration that is ultimately the more appropriate variable to use. And depending on the resistance of movement, this mesophyll conductance of CO2, it can be significantly lower than CI, which can have some pretty significant impacts on that maximum rate of carboxylation that's computed.
The ultimate goal, right, would be a ACC curve.
That's exactly right. Yes. Very good. That's exactly right.
Pat myself on the back.
So CC being chloroplast CO2 concentration.
Right.
Yes, and that would be arguably the more appropriate data set to use. That's right.
I think we really cover two main methods here on how one would measure or estimate mesophyll conductance.
Sure, there actually are three in the literature. One is not covered in great detail in the chapter uh, because it has a lot of error associated with it. So the first method requires no additional measurements beyond what we've already discussed, leaf level gas exchange.
Mm-hmm.
And during the fit of the model, you can also have it estimate GM and therefore CC. So that is one possible method here that requires no additional measurements.
Right.
The two that are mainly in use, two other methods that are mainly in use for estimation of mesophyll conductance involve combination of gas exchange with chlorophyll fluorescence data. And there are a couple of sub-methodologies within that camp.
Sure.
And the second technique involves adding in measurement of discrimination against carbon-13, or the heavier isotope log of CO2.
Right.
And combining leaf level gas exchange with discrimination data also allows for a computation of mesophyll conductance. And there's relative merits and issues with both the chlorophyll fluorescence techniques and the isotopic discrimination techniques.
Yeah, and we will get into those. We won't go into as much detail as the book chapter does, but I think it would be helpful for people to kind of hear an overview of within each method what are some of those sub methodologies that are utilized, and then things to look out for, right? Uncertainties, assumptions, and errors. But before we do, I thought because it's going to be dense, we got to lighten some things up here. A few weeks ago, I was asking some questions of Elizabeth. Yes, that Elizabeth. I was asking her some questions that it was kind of fun and interesting to think about some of these. Hers were about crocheting. Don't worry, I won't be asking you about that. But I do know that you are a lover of cinema. So I was wondering if you could answer a question for me. Instead of trying to test you on movie quotes, which would be pretty hard to do and actually have on air from that movie, I thought I would maybe ask instead of the following directors that I will list for you, who would you want to be gardening with or be in a garden with, right? So I've got four here for you,
All right.
um, and if you could pick one and then also say why.
Okay.
Um, and I think I already have
You
I
already
have
know
a
the
guess.
answer.
I think I have it. Yeah, but it's close. So a first one would be Alfred Hitchcock, Quentin Tarantino, Wes Anderson, and the Coen brothers.
Oh, those are all excellent
I
choices.
I knew you would. I googled snobby directors, and Alfred Hitchcock was there. No, I'm kidding.
Yeah, we just started watching Hitchcock movies with my kids, so it's been.
Which one was the first? What did you watch?
Rear Window was first,
Rear Window. I haven't watched that.
and then Strangers on a Train was our most recent.
That's a good one.
Yeah, it was fun. It was fun. Good villain in that movie. But I would have to pick Wes Anderson of that list. I would think would be a really fun guy to talk to. I think.
That was my guess. So we have already established that there are three methodologies, but today we're gonna focus on the two because I'm the one that's hosting the show and we live by my silly rules. Let's start with PAM fluorescence. Again, with this 30,000-foot view. How does one go about this method? And what is J?
Sure. So there's a lot of considerations to the technique to compute a mesophyll conductance, but the two main camps are using what's called either a variable J estimation or a constant J estimation, where
Right.
J is electron transport rate as computed by a chlorophyll fluorescence measure. And so, as they both imply, in the constant J method, you need a few measurements on a leaf in a region, typically at either saturating or highlight and fairly high carbon dioxide concentration, where J is essentially constant or unchanging. So you need to get some variation in other aspects of the biology, but not electron transport rate
Right.
by definition for that method. And the variable J method is a little bit different in that in order to get a good estimate, you need to force a change over a few measurements in electron transport rate. And that can be done via either, or is typically done via changing carbon dioxide concentration surrounding the leaf in the cuvette.
Right. And so with this method, you need to obviously simultaneously be measuring fluorescence and gas exchange.
Yes, exactly. You do need both gas exchange methods coupled with the PAM fluorometer methods, ideally on the identical same section of leaf. And this is pretty common and pretty commonly available in most commercial gas exchange systems to do that.
Right. And this is not, this is obviously hosted by LI-COR, but the book is equipment agnostic, even though a lot of the drawings show LI-COR equipment. Do we have any helpful like application notes, any tricks that we recommend to folks who are attempting to do this method?
So not really in any of our literature outside of this book chapter. Chapter 11 will walk through all of the details, but there's some great literature on this. These techniques were described in a 1992 paper with Harley was the first author that describes both the
Right.
constant and variable J method, and they describe pretty well the protocols that are useful to determine these parameters.
Yeah. All the more reason to read this chapter,
That's right.
right?
Yeah, the
To
chapter is a good summary of the techniques and does point out the correct references to use if you're really going to make these measurements. That should definitely be read and followed.
gosh, 1992. Would you consider that a long time ago or not that long ago,
Doesn't
Doug?
sound that long ago to me.
You stink. It is too a long time ago.
We should probably discuss. So the mesophyll conductance, as computed from this PAM gas exchange technique, is sensitive to some of the input variables that make it really challenging to get good measurements. And the book chapter goes through that quite nicely, but I'll point out a few that it's pretty sensitive to that include gamma star, or the photocompensation point, which is a parameter that either has to be measured via a different technique, which maybe was discussed in an earlier chapter, or estimated from the literature, or used from the literature, or estimated on the given plant species. But it's good to know that it is sensitive to that. And getting a good estimate of assimilation is also important. It's very sensitive to changes in assimilation too. So you really want to have good, healthy plants typically that have fairly high assimilation rates in order for these measurements to be viable.
What are some things to watch out for? What uncertainties or assumptions or errors should users kind of be cognizant of?
So some things to be aware of. One, you really need fairly large signals because it is sensitive to things like the computed assimilation rate. So if assimilation rates are very small, this method can give very wildly different estimates of mesophyll conductance. And then there's some other parameters such as gamma star that are either measured independently or a literature value is used. And so it's important to consider sensitivity to those as well. There are some fluorometer-specific considerations, such as the wavelength of light used for the measuring beam and the saturating pulse, and how deeply they penetrate the leaf. So the assumption here is that the gas exchange and the fluorescence measurements are over the same section of leaf. And that assumption is not necessarily true, as the light from the fluorescence measurement doesn't necessarily penetrate all the way through the leaf. And there's a lot of good literature on this topic as well.
Yeah, no, that's an important consideration and thing to honestly think about, not just in this case, but as a whole, right?
That's right. Yes, exactly. Yeah, that's a pretty important topic for PAM fluorescence in general.
Yeah, before we move on, Jason wanted me to emphasize that the data that is shown in this chapter was collected by him using that method. So
I'm very proud of him.
let everyone rain praises upon Jason for doing so. It is some good data and it was well done. Getting back to the other, I guess, method, this more, I think we really refer to it in the chapter as the online carbon isotope discrimination, which is a very catchy title for any type of method. But
Mm-hmm.
you covered this a little bit before, but what goes into this online carbon isotope discrimination?
Sure. So it involves subsampling the air streams from both the reference and the sample to a separate analyzer that's measuring not just total CO2 as the LI-6800 analyzers measure, but it independently measures the different isotopologues of carbon dioxide and provides a ratio of them. So as the airstream goes through the cuvette and the leaf preferentially fixes molecules with 12 carbon atom, the airstream will become enriched in 13C. And the quantification of that is what allows us to eventually compute a mesophyll conductance.
If one were to paint with a broad brush, which is what I love to do, which of these methods has more assumptions or more considerations? Or is the answer just yes, they require a lot of information?
Yeah, they both require a lot of information. Yeah, that's a good question. I guess
Doug gave me a compliment.
the chlorophyll fluorescence technique has the huge advantage that there are already commercial systems available that have all of the hardware and software needed, except for the post-processing of data. The big disadvantage with carbon isotope discrimination is there are no commercial systems available to make these measurements, and it's up to users to put together a system to subsample airstreams into this third-party analyzer and handle what are some pretty complex corrections that need to be made, depending on dealing with water vapor and dealing with some artifacts of these carbon isotope log analyzers. And those are very complex corrections that to date are up to users to figure out.
Yeah, it sounds very burdensome. I mean, obviously people do it.
Yes,
right?
And have been for quite a long time. The theory was first discussed, to my knowledge at least, in the Evans and von Kamerer paper from 1986, which really is quite a long time ago.
Which is older than 1992. Thank you, Doug.
So the theory has been out there for a while. There have been labs making these measurements for decades. But like I said, the complexity of the setup is such, and cost, to be frank, cost and complexity of the setup. They often also require fairly expensive and hard to get calibration gases for these isotopolog analyzers.
Yeah, that alone.
That's a big ask for a lot of labs. And so this is not a subject to enter into lightly, right? You really need to have a series of questions that make this equipment important to purchase and set up, and you need to invest the time to both set up the hardware and post-processing of software and multiple data streams is challenging.
Agreed. And to that point, I don't want to belabor this whole section here, but there's a lot of math, a lot of models that are here. Read the chapter to make sense of those. We won't go into that. I won't ask Doug to go into that at this point in time, but maybe if he's willing, talk about the implication of this method on photosynthetic metabolisms, right? So maybe talk about how this method should be treated differently based upon a C3 versus C4 and things that no one else wants to talk to me about, Doug. Only you do, and I appreciate that.
That is another very good question, because C3 and C4 plants have very different isotopic discrimination due to the carbon concentrating mechanisms of C4 plants. So as I said earlier, plants discriminate against the heavier 13C molecules due to the extra mass there. All leaves will have a factor of discrimination as air diffuses through the stomata, from the ambient air into the intercellular airspace. And that's typically considered about 4.4 per mil, if we want to get into details and unit discussions.
Oh, stop it.
So due to the fact that C4 plants concentrate CO2 before fixing it, any resulting fractionation by rubisco, which is the next large step in where fractionation occurs, doesn't really happen in C4 plants. You don't see it. So the amount of discrimination in C4 plants is much lower than the discrimination in C3 plants.
Now, when you say lower, what do you mean?
So So what I mean by that is the resulting discrimination, the difference between the airstreams is reduced in C4 plants. So from a measurement perspective, C4 plants are much more challenging, because the difference in the isotopic signature is much between, say, the sample and the reference is really small in C4 plants. So the signal to noise is higher. The measurements are much more challenging.
Right.
Now, in C3 plants, that's not to say it is not challenging. It's challenging across the board. But because of that larger amount of discrimination, the difference between the sample and the reference lines is significantly larger in C3 plants, making the measurement relatively easy compared to C4 plants.
Yeah.
The other caveat here is the post-processing, the models of the biology to compute mesophyll conductance are completely different between C3 photosynthetic mechanisms and C4 photosynthetic mechanisms. This is an area where the instrumentation to make these measurements can be identical, but the biology to interpret them is wildly different. And that's important to consider. You really need to know your plant material and the photosynthetic pathway to make any sense of these isotopic discrimination measurements.
Right. And we have some resources, or at least places that we point people, right, in this chapter. So please check that out. And for any of the language that's been used here, there will be available a table of these parameters at some point here that we will make available, so you can look these things up and they can be a little bit less foreign. You mentioned challenging a bunch, and which is probably why I liked C4 and continue to like C4 photosynthesis so much. I think I identify with it because I was told that I was, in fact, and continue to be, a very challenging person to be to be around. So maybe that's what it is. But so within this carbon discrimination method, there's, and forgive me if we've already touched on this a little bit, but there's this single point and slope method. What are those differences?
Sure, yeah, there's some key differences there. And I probably didn't emphasize this enough in the section on PAM fluorescence too. The slope method requires multiple data points at different environmental conditions. Typically, it would be a changing CO2 concentration. So you would have multiple data points at multiple CO2 concentrations. And the slope method would fit a line of a couple different parameters there to compute a single mesophyll conductance value. The benefit of that is you can potentially reduce error by having multiple data points
Sure.
and fitting a line to them. The trade-off is it makes a really big assumption that the parameter you're calculating here, namely mesophyll conductance, is not changing over the course of those measurements. And I think there's pretty significant evidence in the literature that that's not always true. So you're making an assumption of a constancy here that may or may not be true. So the other option is to use a singular data point to calculate mesophyll conductance, which is also possible with these techniques, at least the isotope discrimination technique. And again, a trade-off might be increased sensitivity to different parameters and increased noise in the measurement.
So yeah, those methods are quite a bit different, but really everything still comes back to this. It's a complicated measurement, right? There are a lot of assumptions that need to be made. It's tricky. Anytime isotopes are involved, it's kind of a headache, right?
Yeah.
And you know what doesn't give me a headache? We'll return to the podcast after a word from our sponsors. Still buying gold? Cute. While you're stockpiling shiny rocks in your basement, the smart investors are diversifying into plant carbon isotopes. That's right, carbon-13, the stable isotope trusted by photosynthetic systems everywhere. It doesn't crash when the dollar does. It doesn't tarnish, and it actually does something, like fuel biochemical growth. So before you sink another dime into your precious metals, maybe invest in something preciously metabolic. Carbon-13, because you can't photosynthesize with gold, Todd. Well, that was quite a tangent. Let's get back maybe on track here. We have talked a lot about the intricacies with these methods and integrating instrumentation, right? For this method, you need different types of analyzers working in tandem, and it is a difficult thing. What do we mean by this integration of multiple instruments? Like,
Right.
what does that kind of
Yeah,
even look
it's
like for someone to even dream to attempt?
Sure. The first step is that you have to integrate the pneumatics. So there has to be a way to get the flow path from the LI-6800 into this isotopolog analyzer. And even more so, you need to be able to measure both the reference and the sample airstreams. So unlike the LI-6800, where you have two analyzers measuring those airstreams simultaneously, most of the time in this case, you'll have a singular analyzer that toggles back and forth between the reference and the sample airstreams. And the reason for that is due to mostly cost. To purchase two of those analyzers would be prohibitive most of the time. And also the sensitivity of this measurement is such that it may be detrimental to even attempt to use two analyzers to measure them independently. So it
Would
might be the better approach to switch back and forth anyway.
detrimental how?
In terms of any bias between the two measurements would show up in your
I see.
data.
I see.
So if there's any small bias, which the changes here we're talking are very small, could cause problems in your data. So you would need to have some kind of matching scheme regardless, and it's often easier to just use a singular analyzer, especially with the high costs involved.
Is that the main difficulty?
Well, that's just step one, right, of integrating these pneumatics. Now you've got two different data streams, and this third-party isotopolog analyzer is at different points in time measuring sample and reference. So as a user, you have to figure out how to integrate that data stream with your 6800 data. So that's another step. I think another important consideration is water vapor. The sample and reference airstreams have very different water vapor concentrations, and
How different?
up to 20 millimoles per mole with a high transpiration rate and a high assimilation rate. We grow sunflower here quite a bit in our greenhouse, and certainly you can get delta H2Os of 20 millimoles per mole with sunflower. So again, species dependent, but up to really large differences. And switching between those two airstreams would take a very long time to wait for water vapor to settle. You probably don't want to do that.
Yeah.
So you probably need a way to dry the airstream before it reaches your isotopolog analyzer. So that's not a trivial endeavor either. These, like I said earlier, these isotopolog analyzers require a much higher level of calibration than LI-6800 measurements. So you have to figure out a way to calibrate them. So that requires typically some calibration tanks and some additional plumbing and valving. Ideally, you want that process to be somewhat at least automated. So there's quite a bit of infrastructure involved to integrating these flow paths, and then also the data streams too.
Yeah, this is not for the faint of heart. That's why it's in this this part 3, the looking deeper. I mean, these are not trivial methods or even interpretations, right?
That's right.
The breakdown of synchronizing pneumatics, analyzers, toggling back and forth, but then honestly, just as we've talked about, the models themselves are incredibly intricate. There are some variations, but what those mean can also be difficult.
Absolutely. But also can be very rewarding because they can reveal some really interesting insights into the biology. So mesophyll conductance can be a limitation in getting CO2s to the site of chloroplast. It can be a target of improving photosynthetic rates in plants and crop yields. So this is there's some important implications of understanding this parameter better.
Yeah, a very desirable parameter for those who are interested in designing more efficient crops.
That's exactly right. Yeah, that's a key target here. Yeah.
Yeah, so incredibly valuable, also incredibly intricate. For the sake of time, we're coming up on time, and I appreciate you being here and sacrificing some of the time from your day. Can you just give a quick wrap up here? Like, what are some, if a listener and hopefully reader of the chapter could take one major thing away, what do you hope that is?
So I would say that's at least knowledge that the more important or an important parameter is this chloroplast CO2 concentration. And there are some really interesting techniques to quantify that parameter by understanding the resistance of movement of CO2 from that intercellular airspace into the site of the chloroplast. I think that's the important takeaway here, is just be aware of this, oftentimes considered a nuance, but quite important implication of the biology of the structure of leaves.
Awesome. Thank you very much, Dr. Lynch, for joining us and providing this insight.
Happy to be here. Boop. Boop.
Well, thank you again for listening to today's podcast. Please remember to like and subscribe so you don't miss any future episodes. This was episode 9, so we're actually almost done. Please remember to download those chapters so you can get more into the nitty gritty. Well, as always, stay curious, stay kind, and I'll talk to you soon.